In Cambridge, whenever you submit your PhD thesis, you have to put a copy in the library, and they keep track of who's checked it out. And so after 10 years, I went over to the library, and I was super excited. And I thought, how many people have checked out my thesis? And it was one person. And I've always wondered who that one person was, and now I know it was Salim, who read my thesis. Thank you, Salim, for putting my mind at rest. So there was a few spoilers in Salim's talk about what I'm going to talk about. But I wanted to take this opportunity to come here and give you a wider perspective on systems research and a way to combine it with some of the nice theoretical parts of computer science, such as verification, functional programming, and to build real systems and try to get out there to the real world and have some impact. And then circle back afterwards, lick your wounds from the bits that worked and didn't work, internalize some of the lessons and take it back to academia again and continue this cycle. So all of the work I'm presenting here is the result of just a huge amount of collaboration. I've been really privileged to work with and continue to work with some fantastic colleagues, both in industry and academia. And a lot of the work is also somewhat unusually for academia is crystallized into open source technologies as well. So I'll signpost some of the web pages like Mirage.io, OCaml.org, and Unikernel.org, and you can see just a small collection of people we work with. And the key thing that we're trying to get through here is trying to understand what systems research is and how to make a change in the way that we build our systems. So system research has a slightly weird worldview. We're kind of viewed as cowboys, just kind of hacking systems together sometimes, and then putting a few graphs together and trying to publish those in conferences. There is some truth to that, but there's also this ability to take the whole of computer science and to cherry pick, for example, bits of verification or bits of distributed computing or bits of mathematics, and trying to assemble complicated computer systems that, when you look at the whole, all work together. So in my first lecture, I'm going to talk about some of the background, some of the intellectual basis that we've based our systems research on, and that should give you an idea of some of the concepts. In the second one, I'm going to talk about some of the applications into industry. So this is how we pushed this out over the last 15 years to try to make a change in industry. And the last one is going to be about the race to space. It's going to be about how we're pushing this out to the next 1 trillion devices. And some of the more exciting future directions that we're taking this work in now. But first, let's learn about the basics. And the basics started with a very simple, frustrated question in 2003 while procrastinating as a graduate student. And the question was a very simple one. Why are our computer systems getting so bloated all the time? It feels that there's just always bigger and bigger systems that are trying to be downloaded onto all of your devices. If you've looked at the size of your operating system update, there's just gigabytes coming down on your Mac, your iPhone, even your tiny little internet-connected devices. And part of the problem for this is that we tend to kind of tribalize around the way that we build systems. So you look at the code you've written, and other people have written all the things that drives the hardware and all of the low-level pieces that go in there. And this cultural phenomenon is a real problem. Systems has a really, really strange kind of mystique to it. If you look at, which button do I press here? Hopefully this won't turn the whole thing off. There we go. If you look at systems, the folks that bring you the computer, this is, when talking about batch systems from the 60s and 70s, they're the ones who are trying to keep the operating system working. They look like dirty rats to the users of computer systems. They're the ones who understand all the low-level bits of computers. And they deserve more thanks than they get. So this is clearly written by a systems person. How many of you here in this audience have written an operating system kernel or hacked around with Linux and so on? Great. So I make that about maybe 1 in 20 of you. And does this make you any less of a programmer than a systems person? The answer is no. What's happening with systems is that there's just computer code, just like the code you've written, except it's very hard to debug and it's stuck in the innards of a computer system. But this arrogance does permeate through systems programming sometimes. So take Linus Torvalds, the author of Linux. Linux is a monolithic operating system. There was a battle between the different architectures that we were going to use for operating systems. And Linux was a monolithic kernel. We have a microkernel in the form of various research operating systems in the past, Minix, for example. And it's only about 200 kilobytes. So that's pretty much, it's portable. It's for this tiny kernel. It's about how big you can get, and I can rewrite it from scratch. Great. So of course, as time goes on, Linux has over 25 million lines of code that goes into every single device that use it. A lot of it is essential code. A lot of it can be stripped out, but there's still just a vast body of code. I think it's safe to say now that the architecture that began as a portable, rewritable in a weekend type operating system is no longer that. It's become this huge establishment way of building code. And Windows it just goes out there. These are numbers from 2015, and generally as a rule, as you can see from these graphs, the number of lines of code only ever increases. So these systems are gathering steam, and the high-level thing I want to figure out is this something that we're stuck with forever, or is there some way we can change the way that this works? And here's the fundamental problem. There's code that the vast majority of you in this room have written. You've typed into your editor. It expresses the complicated logical algorithm that you're trying to build to get your job done. And then underneath the tip of the iceberg that you've written, there's vast amounts of growing code that is dragging down your system, that your operating system, your frameworks, they all insist you need. And we want to figure out, will this iceberg ever get bigger and bigger and bigger? Will we end up in a few hundred years becoming kind of archaeologists that do nothing but dig through layers and layers of computation in order to figure out what is going on under the hood? Many of you, I'm 40 years old, I can identify with about these layers. I have to go talk to Cambridge and Glaswegian and Berkeley professors to talk about what happened here. When you get to here, sadly, many of the pioneers of the time have now passed away. So we really are starting to already become these kind of archaeologists, trying to figure out what's going on in our computer systems. This can't continue beyond the next few generations. In many ways, computer science is a bit like being a biologist when Charles Darwin was still alive. We can see the snapshot of incredible growth, and we have this opportunity in front of us right now to try to understand, learn from the people who built the first computers, and to make sure that the next kind of 100 years, which is longer than the entire length of our industry, is actually one on a sustainable footing for the future of society. So we need to understand what a modern software stack actually looks like before we can start fixing the problem. Where are we? It's pretty simple. We start off with some hardware, and you tend to build an application. And what we have are two major software-based abstractions between these things. One is the idea of processes, and these processes are a single unit of computation that runs in its own isolated address space. And this is all mediated by the kernel, the grand oversight in the sky that runs in every modern computer, and it provides a bunch of basic services that acts as a layer between the hardware and between the user. Now, how many of you have done an operating systems course and are comfortable with operating system concepts? So put your hand up if you're comfortable with processes and address spaces. Great. So there's about half of you. For the other half, if you're completely lost, put your hand up and I'll figure out a prize for the first person to ask a question. The basic essence of the kernel is that it drives the hardware and software. It acts as middleware, and it implements a series of complicated services. And these services tend to abstract you away from the raw details of the hardware. So if you have, for example, a USB drive or a spinning hard drive or a network storage connected device, then the kernel is responsible for taking the hardware, driving it, and then providing you with abstractions that give you a much, much easier and consistent thing to consume so that your applications don't need to know about the details of all the hardware. Once it's built those abstractions, and this is true, for example, for the networking stack, where things like wireless connectivity, TCP/IP for networking, all the way down to Ethernet level connectivity, all these are provided by the kernel. And then when you need to perform some scheduling, which is given a series of things in the computer, I need to figure out when to do things and when to drive them. The kernel is responsible for that. It ultimately mediates all of the hardware and translates the events happening in the outside world into events that can be consumed by applications and sent backwards and to the outside world. And perhaps its most important thing is isolation, which is a vast amount of energy is expended by the kernel to make sure that it can run isolated processes that cannot interfere with each other beyond the security policies that the kernel has implemented. So, and these security policies can obviously be quite complex, and that's completely fine. The kernel just gets more and more complex and elaborate with how it performs that isolation. So these are the basic requirements of the kernel. Now, along the years, this basic architecture has not changed for the last 60 years. Hardware has become much, much more complicated. So I notice here lots and lots of laptops. So just counting the number of cores in this room, there's probably 1,000 cores running in this room. Just In fact, I'll up that actually if many of you have phones, because there's now 4 processors in the modern mobile phone. Every laptop has 2 to 4 processors and multiple co-processors. And the nature of the memory has changed as well. So just on my person, I'm carrying more memory in my watch, in my phone, in my laptop, than the sum of all of my computers that I've ever owned put together in the past. It's just vast amounts of resources are available. And so the operating system, explains some of the growth in the operating system, because it's got to deal with all of this complexity. And when you look at it, I was very harsh towards operating systems when I opened the talk, but in fact they're wonderful pieces of engineering, because they can take this diversity of things that we've had for the last 40 years, the things that we've built and deployed, and the device driver abstractions can deal with that and more or less run our applications with a fair degree of reliability. That's good engineering, but it also explains why so much complexity is increasing into that operating system. Now, what the kernel does is it needs to communicate with the processes. It needs to talk to the various processes running inside the machine in order to figure out what they want to do. And so remember, when you're a process running inside an operating system, you're kind of in a womb. You have no idea what's going on in the outside world. All you can do is you can run some code, and when you run the code, you then eventually want to talk to the outside world or see some resources from a file system. You might want to make a sound through a sound device. And to do that, you need to invoke a function call into the operating system. And the operating system looks at what you're trying to do. It looks at the state that is gathered about you. So it gathers everything it knows about your privilege, the amount of resources you've been assigned, any kind of limits, all of that stuff. And then you can make a function call to it, knows the system call. And what the system call does is that it's a very low-level call that is implemented through, either through some hardware trap or often through software as well. And it's just a function call, but it's a dynamically dispatched function call. It's got a very well-defined interface. And that function call is responsible for the kernel receiving what you want. It then keeps you at arm's length. It doesn't trust anything you say because you're a process that is running at a lower privilege level. And it then figures out what you want. It might, for example, make a network connection, and then it sends it back to you. So the only thing you can see from the outside world in this kernel interface are things happening through system calls or another interface known as ioctls. By and large, the kernel mediates all of the side effects in a process. So it's got to set up connections. So for example, it will set up a network connection, and then it will allow you to send traffic down the connection, and it tries to get out of the way so that it doesn't slow the connection down too much. And so it's only whenever it needs to authenticate or check something that it gets over there. Now, this interface seems like a relatively simple interface, but there are hundreds of system calls now. So the interface to the kernel has become wider and wider and wider as the years have gone by. So it started off, you can build very simple operating systems with just a few system calls. And now if you look at the various things available in Linux, many of them are never used. They're used for very obscure, often in many cases legacy uses. But each of them are available to you to call. So it's a bit like being in this room, except that there's actually 1,000 shadows here in the room as well. And they're not participating in this conversation. They're just looming. They're just looming for some reason. And you think, well, don't worry, they won't do anything. They're just sitting there and they're just hanging out. But they add weight to the entire conversation, because whenever we're here and we're interacting, then you can see that you know exactly what we're dealing with. But if there's all these invisible system calls and interfaces available out there, they all form part of the attack surface. So a bug in any one of those things can result in the entire system being compromised. And the reason they hang around is because Linux is such a well-established operating system in Windows. Every system call forms the interface to the operating system. So every time you run an executable, it is invoking those system calls. So they can never deprecate one of those calls. If they add one, if you work in Linux, it's open source, and you add a patch and you submit it there, and that turns out to be a system call that is perhaps not that useful, and they replace it with a new one, they can never change it easily. They have to keep it forever. So this explains why Linux is getting so much weight as time goes on. And then your applications themselves, they don't directly make system calls. In fact, they have these libraries. And what these libraries do is that they abstract the low-level interface behind the system calls with slightly higher-level interfaces based in the C programming language. And there's many standards that define how to write portable code. So whenever you write, for example, your first network stack or a little database server, or in fact anything that uses kind of modern C, it's using a standard called POSIX in Unix-like operating system. When you, for example, open a file descriptor or you send and receive from a socket. And these standards try to be portable. They try to be across Unix-like systems like Solaris, Linux, Mac OS, the FreeBSD, OpenBSD, NetBSD family. All of these Unix variants try to maintain homogeneity. Behind the scenes, the POSIX interface is the same, but the details of the system calls vary widely across operating systems. So this forms a nice abstraction layer where you compile it for an operating system, your application, and then it can run your code. And then your applications finally link to all of this stuff. They link to it's known as the libc, the system C library that implements a lot of this functionality. And then we've finally gotten to your logic. Great. So this is now the code you've written. You can see why it's going through so many layers in order to do what seems to be even the simplest thing. And the poor kernel here, it's dealing with hardware that's ever-changing. It's dealing with applications that have been written 30 years ago that it's still got to execute, all going through this kind of system call interface. And it's trying to make the best use of all the hardware. And all it knows about the hardware is the device driver kind of mappings that it has available to it. And sometimes it doesn't even know it's hardware. If you hot plug in a USB device, think about what your poor kernel has to do. It's suddenly got to rewire all of your hardware routes. It's got to explain to its applications running that this new resource is available. And what if by the time it's done that, you've just unplugged it again and everything's gone? It's got to deal with so many things asynchronously behind the hood. And the problem is the scheduling is very difficult if the applications don't cooperate. And applications in the conventional world are extremely uncooperative. They're demanding. They're like a small child just sitting there, insisting on getting some resources, spinning away, trying to take as much of the CPU time as they can, and they just don't care or indeed know about what is happening within the kernel. So there's a real lack of cooperation happening there. And so, for example, if you write your application, say in Node.js, and you're only using one core, then the kernel cannot magically lift that logic into working across multiple cores. The resources will just be wasted. And so, in the grand tradition of these kind of systems, we couldn't fix the kernel. We couldn't fix the applications. No one agreed to get along. So the answer is just add another layer, right? And that'll fix all the problems. So another layer is known as a hypervisor. And the hypervisor was a supercutting solution in the early 2000s to say, well, we have these physical computers, and the hardware we have is getting more parallel, more diverse, more flexible, but our applications are not really changing, and we're struggling to keep up with making sure that a computer that is getting bigger is fully utilized. So why don't we just lie to the kernels and say, here is a portion of a computer, a virtual machine, and we will carve up the physical resources with tiny, thin software layer, and then we will make sure that we can run multiple virtual machines on these on the single physical computer, and thereby start multiplexing more logic on the same physical hardware. And you also have some cool things, like you can just dynamically spin up and spin down virtual machines. You can give them more RAM. You can spin them down, and so you can take services that perhaps ran inside an old data center with each computer running at 10% utilization, run them on one machine, one modern machine that's more power efficient, running with virtual machines. So this is a technology that just took the IT industry by storm because just so much money got saved by doing this. So it highlights just how inefficient the application and kernel communication was, that there's billions of dollars that were saved just by doing this. So the Xen hypervisor is one of the premier open source hypervisors that powers the cloud. When it started, it was a grant proposal so we could play Quake together. And the idea is that I don't want to run the server and I don't want my opponent to run the server. Can we rent something in between that is a fair kind of latency between both of us? And that marketplace, well, our marketplace never got anywhere. The hypervisor did. And companies like Amazon, Google, Microsoft are all building what's known as a cloud now, where you can run on millions of these physical computers. So this layer provides us with the ability to kind of fake the kernel. Now, the way it works, I'll go into this in more detail in my second lecture, is that the hardware that was formerly running on hardware is now given a virtual equivalent. So the only thing Xen does, it virtualizes the interrupts, which tell you when something happens in the outside world from a device, and then the memory in the computer and the CPUs. It doesn't actually know anything about device drivers and so on. It delegates those to guests that are running and supplying the various abstractions. And then the great thing about it, the reason it became so good, is that the only thing you had to patch was the brain of the operating system, the kernel. You didn't have to touch applications. You didn't have to touch user space. You didn't have to touch libraries. All you had to do is modify Linux with a tiny targeted kind of ninja patch right in the middle of its notion of what hardware it was running on, and make it just make software calls instead into Xen. And then this way, instead of having to deal with all kinds of complicated traps and emulation and so on, Linux just told us when it needed some resources at the lowest level of manipulating its address spaces, and Xen would just deal with that, and it would multiplex them and make it all run. This is a technique known as paravirtualization. And the reason it became so big is that everything else is completely unchanged and just continues to work. So your applications run in a virtual machine, and by and large, you're running on the bare metal, and they're supplying just enough information to continue their operation, and then you can figure out how much of the memory they're using, and then give it more virtual machine resources as required. So this layer was pretty successful. But then it got adopted at a vast rate, and we noticed there's some fighting going on. People just weren't getting along. And what's happening is that the hypervisor is running its own scheduler, because it's got to schedule the virtual machines. And then the kernel is running its own scheduler. It's got to schedule its own kernel threads, all of the different service abstractions running inside, like its file system and storage. And then the processes, well, they're running their own scheduler too, right? Because you might be running a Java virtual machine or something else. It's running its own kind of user space threading processes. It's also going to manage the application level logic. And then you've got your actual business logic, your application, and it's got its own scheduler as well, at perhaps a different level. And all of these things are not cooperating in their scheduling. So the result of this is that you have this kind of lack of harmony whenever you're processing data, because you might just be doing something, then you get distracted and you have to do something else. And then all of your caches are the things that manage to keep modern computers fast are all just being destroyed, because the application has no kind of focus, no flow in how it's doing its work. And this multiplex scheduling has long been considered harmful. It's considered harmful in networking. It's considered harmful in storage. It's considered harmful in operating systems at all, because it means that your system is not being used to its maximum efficiency. But then, we're going to fix this by adding another layer, because that's what the industry does. We're going to fix multiplex scheduling by going off and saying that we need another abstraction that's even more lightweight than the previous one, but we're going to keep the previous one anyway, because it's being used and deployed by lots of people. So this is what containers are known as. How many people here have heard of containers? Oh, lots and lots of you. Good. It's a good, well-hyped thing. Good area to get a job in right now. But what containers are fundamentally is a level of virtualization, not between the hardware and the kernel, but between the kernel and between user space. So it's saying that we would like to share the kernel actually, because I have a few apps that just they don't need to have a full kind of virtual machine that's big and heavyweight. I just want to run a little bit of lightweight isolation. I don't mind if they share the kernel, because I trust the kernel. But what I really want is the ability to have millions of these things without having to assign memory and CPU resources. I just want to make it more declarative. And what a container does is that it provides a namespace, a grouping where it can pretend from the kernel perspective that a system call, for example, to a file system is in a particular namespace. So it's isolated from all of the other namespaces. And it lets you detach these namespaces so that you can say, I would like to run my web server inside its own domain where it cannot see any other processes running in the machine because they just don't exist inside its namespace. But behind the scenes, it's just a lightweight translation so that the kernel can then continue to do its work. So one of the big systems, known as Docker, is a container manager, and launched in 2014, and it's one of the fastest growing technologies on the planet in terms of adoption in data centers and IT. So just had its, I think it's 2013 it might have been funded officially, but the growth is just insane. It's just billions and billions of access to the central repository. And so each of these layers is clearly solving a problem. I've talked about Xen just being deployed in billions of virtual machines, Docker being also just deployed in just billions of containers being deployed by Google, by Amazon, by Microsoft, and so on. But where is this all going? What is going on? Like, are we just going to end up with more and more of these things? In the application space, JavaScript, has anyone tried to write some JavaScript code recently? Yeah, I see a few. Do I see smiles or do I see frowns? I mean, it's just complicated. Then you have something called WebAssembly, which is a new runtime for the browser. So the browser is becoming a new hardware platform. And then you have JVM and .NET with its own ecosystem and its own complexity. And then you have, on the embedded space, you have the microvisor from ARM, which is kind of a hypervisor, but it's micro. And the great visor, which I made up, and the ultravisor, which just sounds cool. I mean, all these things are coming along. We have FPGAs, we have AI chips in our phones. What is going on? are we just doomed to just keep figuring this out? Is your computer science course going to get longer and longer and longer until we're all just old? The answer is no. Like, we have to figure out how to fix this. And if you identify the systemic problem, the problem is systems programming has been divided from application programming. There's been huge amounts of innovation in both. But systems programming is still confined to C. The kernel is still stuck in its own world. There's special tooling. There's very little code reuse between kernel code and the application code that you see. So when you submit a kernel patch, you're a special person, mainly because you just can't use any of all the other work you've done in the past. It's ridiculous. And possibly the worst thing is that there's awful debugging support. So the barrier to entry is really high because you have to know all of this stuff and keep it in your head because you can't even get some output from the console just because no one's added a debugger to the system. And fundamentally, it's just a monolith that's formed its own little universe. In contrast, application software is quite good fun. We've seen vast numbers of new languages, new innovations, new IDEs and tools. It's taken over almost every part of modern society with the way that we work. We've seen new languages like Rust, like Go, OCaml, which I'll talk quite a lot about, Haskell, Lua, Idris, if Edwin Brady's in the room. It's a wonderful language he was trying last night. Swift from Apple, D, which is a new programming language. And it feels like these languages are actually just being constructed and synthesized and released by megacorps and by researchers almost just monthly. You can get a major new language. So, and each of these languages are almost domain-specific languages. They solve a particular niche that they're trying to address. So Rust, for example, is great. It started as rewrite a browser in a safe language that isn't C, and try to have no runtime whatsoever. Go is trying to build lightweight concurrent distributed systems from an old OS heritage, a very rich one known as Plan 9. OCaml is trying to be a functional but pragmatic language. And Haskell is trying to be the essence of functional programming with no mutability except under control. And things like Lua are highly embeddable. And so each of these has spawned its own ecosystem and its own wonderful new world. So how many of you have written in C in the last year? Okay. How many of you have done it as part of a course, and how many of you have chosen to do it? Okay, that's like none of you have chosen to do it. How many of you have written in one of these new modern languages that's in a kind of a high-level language, or Java or .NET, something that isn't C? Yeah, it keeps going up. And so this has gone up. And if you try to do something for your own purposes, chances are you'd use one of these new languages, not C. So we have to close this divide. And this is what I'm going to spend the remainder of the time talking about, which is how do we get the best of both development worlds? If we can close this gap, if we can just force these communities to talk to each other, if we have just enough operating systems so we can choose the level of complexity that we work with, if we can use this wonderful new application tooling, figure out how to get this zeitgeist of people who are doing work in this space together, and then we can fix systems programming together, and we can try to have a future where we don't have great ultra mega visors that we have to deal with and many layers of complexity. And it's great to be here in particular because the answer, it turns out, when you start doing a bit of research, started to emerge from Cambridge and Scotland in the late 90s. So Glasgow and St Andrews had a long history of doing interesting research in building new operating systems. And let me give you a little bit of background into how this works. So whenever you have one of these conventional operating systems that I talk about, you've got your hardware, you've got your kernel. Then inside the process, you have its own kind of layers of abstractions for how to build the application that you're trying to build. So in the case of a Java machine, for example, you might have the bytecode. You might have an executable that you've compiled, which is the actual native code Java virtual machine. And then you've got all these libraries I talked about, which let you interact with the system below in order to make it all work. And this is a very kind of prescriptive process, right? There's no choice here. You have to obey this particular architecture in order to work with this operating system, with Linux or with Windows. That's it. Library operating systems were a completely different architecture. And what they said was, hang on. Do we really need to force an application into separate address spaces, into this kind of process model, using this particular standard of POSIX APIs that were kind of organically developed in the 70s and 80s by operating system vendors? Is this really necessary? What we can do instead is we can take all of the pieces that drove the kernel, Like, for example, I said it's got services and device drivers and schedulers and so on, and turn them all into libraries. And these libraries are just ordinary libraries that you might use, like linking to an SSL library for secure communication or a MADS library, or just break up the big code, take a digital ice pick to it, and try to break it up in these libraries. And at the end of it, there's no kernel left. There's just function calls into other parts of the kernel. And then all of the device drivers, the schedulers, the thing that your application was formerly dynamically calling into can now just be called as function calls instead. And they can be linked directly into your application. So the applications select the libraries they need, they just link them as normal, and whenever you wanted to make a function call, instead of dynamically dispatching it, you just keep compiling. Your compiler just keeps going. And critically, whenever you run this thing, your application has effectively become an operating system. The application, because it's now linked in with the kernel, just like it's linked in with other application logic, drives the hardware directly. So there's no layers between us anymore, and hence it's called a library operating system. So the implications of this are huge. It means that we don't have multiple processes anymore. Processes are an abstraction kind of enforced by the hardware. So it's a very useful way to do lightweight isolation. But there's no reason why an application can't decide to use processes in a way unique to it. It doesn't have to fit into this process model if it doesn't want to. So a library operating system eliminates by default the notion of address spaces as an enforcement of isolation. And it makes the hardware available to the application to use as it sees fit, because the hardware is now free. And it turns all of that into a library. So this application now becomes a single kernel driving the hardware directly, where the kernel is now transformed as well into different bits of libraries. So the application that we've now built with a library operating system, and this is in the 90s, runs in a single address space. It's got a single calling convention. This is so much fun, because when you have a single calling convention, if you work in compilers, it means that you can compile the whole application as one holistic piece, and then try to optimize it across everything. It also means it's much easier to reason about, because we don't have 5 different mechanisms of syscalls, of ioctls, of mmap. All of these might be words that you see in manual pages, but haven't quite come across, and that's because they are quite complicated and unnecessary in many cases. If we were to rethink the way that we construct an operating system, we wouldn't necessarily use all of the legacy interfaces of the past. We'd come with new, interesting, and simpler and more consistent calling conventions based on what we want to run inside the application stack itself. The previous ones are all built by layering and accretion over the decades. So the pros of a library operating system are you have application level control over hardware. If you're building, for example, a database, you want to precisely understand when you've written something to disk, so that you know exactly what the level of consistency that you have is. If you're building a web server, you just want to send billions of packets as quickly as you possibly can. Only your application really knows what it needs from the hardware. And the library operating system provides you with just enough device driver abstraction to not make you go insane, because you have to deal with all the details of the hardware, but enough control over the innards that you can have it if you want to. The problem is that there's no kernel protection internally. The kernel protection protects you from yourself as well, from bugs in yourself. So if you don't have that, then it is a problem. And so in the 90s, we had 2. One called Nemesis, which came from Cambridge and Glasgow, and from MIT came the Exokernel, and these are both library operating systems. And none of them succeeded outside of academia, because there's this huge kind of bit rot problem of device drivers, where to actually run the hardware, Linux has thousands of contributors, because they all combine together to work in open source in order to support all the latest hardware. With the library operating system, we've just gone and enthusiastically taken it apart, removed all these abstractions, turned them into libraries, wait a year, nothing will work on any modern hardware, because it doesn't have that kind of momentum and network effect to keep it going. But it did become popular in niche areas. So if you built network appliances, for example, the Cisco boxes, or it's called NetApp for storage boxes, or if you do high-frequency trading, you might work in this kind of space where you have a lot of control over the operating system. So it had benefits, but the idea just never took off. In 2010, though, with the advent of Xen, we had a bit of a breakthrough. The device drivers, which formerly we had to keep running on each individual machine, we're only seeing virtual devices now, because we're running on the cloud. So if you're running on the cloud, you have this thin layer known as Xen, and it is abstracted by it's abstracting many of the details of the hardware. And also the need to log into a machine interactively had largely disappeared by 2010. So if any of you remember the old days where you'd set up a single big Solaris machine or a big Windows machine and handcraft it to make sure that all the settings are right and look at all of the internal things and do all that stuff, it's all gone. Because now with virtual machines, you just spawn a new virtual machine, you destroy it when you don't need it, and you don't have to worry about all the details of how these things work. So the industry had moved towards a model where you don't have one machine doing many things. They became single-purpose virtual machines that just do one thing and try to do it well. And so the drawback of library operating systems is no longer a drawback because we just want to build these appliances that just go and do one thing. And we also had a software interface to hardware. So on Amazon, on Microsoft, on the various clouds, I could just make an API call with a web request and have a virtual machine running. I have, in the past, spun up hundreds of thousands of cores with a shell script that's just lashed up in a matter of seconds on my laptop. So it's an incredible amount of power through just using software. I didn't have to go and plug in machines in, do any of that stuff. And this is where the essence of unikernels came in. The idea about unikernels is really quite straightforward, given all these concepts. Often in systems research, the trick is look through all the noise and try to figure out what is the simplest way you can achieve the goal that you want. And the goal we wanted was to make it easy to pick high-level languages and to build specialized operating systems from them in order to get various benefits I'll talk about. So what unikernels do is that they take the source code, you compile your application source code into object files using your normal compiler, then you link in various libraries into it for the services you need, and then you link in a boot library, which basically starts off the unikernel, and then you take the configuration of your application as well. So not just a generic application, you tell it, I want to run at this port, I want my website to have this name, and you then compile the whole thing together. It's all written in one language, and then you output a tiny little microkernel, which is the bare minimum thing required to, given all of this information, given a whole bunch of compilation, to run in as optimal way as possible. This thing is so focused. It has it's like a horse, with the things in it. It's just running, sprinting for the end line, and it doesn't know how to do anything else. If you want to change anything about it, you've got to change your config files, change your code, recompile the whole thing, and deploy it again. In return, though, you get a very specialized kind of small thing. And so what these unikernels do is that they combine high-level languages, the languages that I told you about, the OCaml, the Rust, and those kind of languages, the Haskell, for example, with libraries in order to build very specialized operating systems. And critically, you can exploit modern hypervisors so that instead of trying to target the millions and millions of hardware devices out there, we can just simply target virtual hardware libraries. So we only had to build a few sets of libraries, one for VMware, one for Xen, one for KVM, and not one for every USB device on the planet. And we wanted to leverage all of the nice high-level features so that we could start reasoning about our applications as well. So you can say, for example, given my web server only listens on port 80 and port 443 for SSL, why do I need all of this complicated logic in my networking stack to deal with lots of data structures for dealing with applications that listen on hundreds of ports or thousands of ports? It's just unnecessary. So in theory, you could rewrite the application so that it constant optimizes for just those two ports and nothing else. And so these techniques became open to us because of unikernels. So they're really easy to run in the public cloud. And the initial prototypes, they could boot in milliseconds. So it wasn't a matter of just taking seconds to boot looking at Linux. They would boot in almost instantaneously, because the only thing a unikernel needs to do is to jump into the start of its address space, start executing. There's no hardware discovery or setup. It's all so specialized. The images are so tiny that in 2011, we built, for example, a DNS server that could run the root name services in the internet. And it wasn't gigabytes in size. It wasn't megabytes in size. It was kilobytes in size. It was 180 kilobytes to run all of the logic around the DNS protocol which runs the internet. And not only was it many, many kilobytes in size, but it was also incredibly safe because it had almost no C code running in it as well. And it was also one of the fastest servers on the planet. I'll come back to the various cons about standards and so on in a bit. But the biggest concern in library operating systems was the security of the single address space. How do we get over that? So we have to build tons and tons of code to make these unikernels work, right? I said we're going to have to break up operating systems with millions of lines of code into libraries. But even if we did that, if we succeeded beyond our wildest imagination, if I broke up Linux and I had it all printed out in front of me as libraries, have I really won? Well, it's a lot of C code. It's a lot of sources of insecurity through low-level attacks that we hear about every single day. So what if, while we're here, while we're rewriting operating systems, we just rethought fundamentally what the interface to the outside world should look like? And so this is what Mirage OS is. Mirage OS was continuing this whole idea of unikernels and libraries and linking into operating systems, but rewrite these very flat function calls into composable and modular interfaces and implementations. So this way, you can rebuild it in a style amenable to verification and reasoning because you want to write it in as mathematical a style as possible. It's not possible to write the whole thing so it's amenable to formal verification, not yet, but hopefully quite soon. But we can rewrite it in that style, so we're kind of heading in that direction. But also friendly to normal, ordinary mortals. How many of you here have done any functional programming? Oh, I can tell Idris and Edwin have been lecturing here recently. This is great. How many of you would think to apply it to, for example, building a website? A few of you, good, it's extremely encouraging, normally 0, but I saw about 10 hands rise. It's not something you normally associate with building real systems. The choice of language that we picked was one called OCaml. And what OCaml is, it's an industrial-grade mixed-style functional language, which means that it pretty much tries to do all of the things. It's got objects, that's the O in OCaml. It's got imperative programming, so it's got variables that you can mutate, but you have to flag the variables which can change with a mutable thing. So it's strictly evaluated by default, so it's not lazy like Haskell or so that whenever you write some code, it's immediately evaluated unless you choose to make it lazy. And it comes from a very, very rich heritage of ML-style programming, which actually, again, came from Cambridge in Scotland. So Robin Milner was in Edinburgh for many, many years, and then became the head of the computer lab in Cambridge. And he designed this whole ML family of programming languages as a mechanism to make it work with his LCF theorem provers in the early days. And OCaml is characterized by an unusual pragmatism in functional languages. It has one of the most powerful module systems on the planet, which means that you can build large-scale abstractions, which I'll describe to you shortly. And then you can also compile to native code. So the end result eliminates all of the types at compilation time. So all of the restrictions in various bits of the code that you put in just disappear once you compile it. And the end result looks like a tiny little runtime, a little garbage collector, but it looks a lot like C code, like when you look at the actual output of the compilation. So we have this wonderful kind of mix of big, lofty kind of functional abstractions, and then really fast binaries that look very much like the things you want to run in an operating system. So I'm going to dive into a little bit of OCaml now. So everyone get your operating system hats off and your functional programming hats on. OCaml. Has everyone seen OCaml before? I assume you've not been taught OCaml, but you've been taught Haskell or Idris or similar languages. Is that, yeah, I see a few nods. So in OCaml, we have a few little quirky bits of syntax. One of them is that you have this let syntax. So I can say let x equals 1 and let y equals a string called world. Then I can define a function here, and the function says, given an argument a, convert a string, a decimal in a string, and return a string, and then print the result for hello. And what it has is that, so he's got these variable names, and you can define functions by these let bindings, and then you can print the result. This is known as a signature. So every single value here has a type. So the type can be just a constant value like an int or a string, or it can be a function. So in this case, fn takes a string function and returns a string. And obviously you can have more arguments as you go along. And mixing types up results in a compile time error. So in this case, I'm trying to add x and y. X is an int, y is a string. It says, well, I'm sorry, my plus operator is only an integer, so therefore I can't add an int and a string together. I'm going to reject your program. So your program has a type check. And in many ML programs, there's some beautiful theorems like parametricity and principal typing and so on that let you start getting theorems for free whenever you respect the type system. So there's the ability to work within the constraints imposed by the language. reason about assertions and preconditions in your program within the limits of the power of the type system, and then have them all disappear. So there's no overheads for these abstractions at runtime where at all possible. So that's the essence of OCaml. It's a very pragmatic type raising language. So what does a hello world look like if you're building it in this kind of unikernel style? What we're going to do is we're going to build a little unikernel, and then we're going to progressively turn that into something that will run as a standalone operating system. And hopefully you can see that if you were writing OCaml code to solve your problems, that as a developer, you don't need to know anything about systems programming or kernels or all of that stuff. You can all become operating system hackers just by using this framework. So our little hello world has turned into a logs call. And what the logs library does is just a normal OCaml library. And it does lazy logging, and then it converts its argument into something that can be logged, obviously, to the outside world as an informational log. Now, what this syntax here is saying that instead of passing in a logging string, we're passing in a higher order function. And what this higher order function is a closure that is not evaluated. It's simply a function being passed around as a value. And that when this is given an argument fn, it will then proceed to evaluate it. And the reason for this is that you want to put logging everywhere in your program, but you don't want to slow down the program by logging all the time. So in C, you might use a preprocessor or something to avoid doing that. In OCaml, you simply say that I'm going to wrap the logging call in a closure, and then whenever it needs to be evaluated, it will be evaluated. And the function being passed into it is itself a function, which when it receives a logging string, will then log it. So you can see how in our hello world, we're starting to use higher order programming in order to build nice functional abstractions for something as pedestrian as logging, which it turns out is quite a difficult problem. So now what we do is we want to just make our hello world loop recursively. So the first program, all it needed to know was it just printed to the console. It didn't do very much at all. But now we want to introduce the notion of recursion, where I can take my logs call, I'll sleep for a second, and then I'll loop back to hello again. And the rec here simply says that this value can be marked as a recursive value. This is a slight problem though, right? Is that all I want to do is sleep for a second. It's a common desire. And it's pulled in the entirety of our 25 million lines of code of the operating system, just because I've made a reference to Unix, and now I need all of the things. Do we really need 50 million lines of code to sleep for a second? It shouldn't be necessary to have this much ambient information, right? So what Mirage OS does is that it takes a lot of the logic inside the operating system and lifts it into itself, into the implementation as a library within OCaml. And the first choice we made was to try to ditch many of the prescriptive abstractions in operating systems that are forced on you. So one example is threading. If you use threading, Susmit here lectures the concurrency course in St. Andrews. Very, very complicated topic. And to some extent, unnecessarily complicated, because we're dealing with other people's notions of concurrency and mapping them onto our desires for concurrency. So this mismatch is a common theme in systems, leads to vast amounts of complexity. But if you're just starting from scratch, we can say, for example, I don't want to have preemptive threading. I want to have just my application within itself, deciding for itself exactly when it switches between function calls and so on. So this is known as cooperative threading. And when you use cooperative threading, if you can all get along within your source code, then you remove a large amount of logic in the application that deals with switching and so on and so forth in order to pull all these to pull all the preemption logic together. It happens because the operating system doesn't trust the application to yield in time, and therefore it'll force it to yield. And then this leads to the application have to deal with just being rescheduled at random times, and everyone ends up being very defensive. So in OCaml, Achako Jerome wrote a cooperative threading library, and because we're in a functional programming language, it's a lovely way to express these abstractions natively in the language. We didn't need to modify OCaml at all to support this. And what's happening here is that it's like our previous hello world, except we're doing something called a bind. And what this bind does is saying that I want you to sleep for a second, and then whenever the sleeping is finished, I want you to then call this function in a chain afterwards. And then LWT, the library threading library, will take care of figuring out exactly when it needs to wake up this particular thing. So we can take advantage of the fact that we have functional programming to say that I want to declare my intention to sleep, and I'll tell you what to do next in the form of a promise. If you've done any JavaScript and Node.js programming, they should be very familiar. They're the kind of callback style of programming, which is very common in reactive systems. Except that instead of writing callbacks manually, we can use these promises to abstract away within a language all of the sequencing of concurrency. And so in this one, something in the outside world will take care of sleeping for a second, and then later on, it will call hello. This is a slightly awkward way to write things. So a cool thing in OCaml, you can define operators. So I can say that I replaced the bind earlier with an operator called greater than equals. And this is looking much more natural. We just had to replace our semicolon with this operator. And then suddenly we have a corporately threaded library that expresses the essence of what we want, the essence of trying to sleep for a second. But it's formed a data structure within OCaml that describes the timing requirements and so on of the program. And so obviously I'm not going to go into the details of exactly how LWD works, but what this is known as a concurrency monad. In many ways, it's an incorrect term because it's not actually a monad. It doesn't obey the monad laws, but that's what it's called. And the great thing about it is that it scales massively. You can build millions and millions of these threads, but because they're native to the language, they can be optimized and compiled away just like any other feature of the language. So we've again taken something that was outside in the operating system and lifted it into our kernel. So now we have a fairly portable bit of code. That pesky reference to Unix has disappeared. So it's a relatively portable hello world, and we're going to implement this as a unikernel. And what we've done here is I'm introducing the module system in OCaml now. What this module system does is that it defines a function called start, which is the life cycle of the unikernel. It says that when you start, I want you to sleep for this many nanoseconds. And I'm going to take a duration, which is a library in OCaml, to calculate durations and convert between nanoseconds and microseconds and so on. And I want you to sleep for this amount of time. And so this looks very much like the previous code, except it's calling a module called time. And time is not Unix.time. It's something that we're requesting from the outside world. And so in OCaml, what you can do is you can say, I can define a module called hello, except this module depends on another module called time, which needs to be supplied to it. And this time has to have a specific set of signatures and so on around it that define functions within the time module. So here you can see, for example, this time module has something called sleep for nanoseconds, but we don't know anything about the detailed implementation of time. This could be in Unix. It could be inside a custom operating system. It could be in a web browser. It might even be in an FPGA. All it has to do is have some notion of sleeping for this amount of time. So we've isolated just the piece we need from the operating system. What that looks like is, in our hello world, is that we have this hello time implementation, and the signature, the description of what it is very, very abstract. It's simply saying the module type of time is some mechanism for blocking I/O. So this is our LWT library, for example. And then a function that just says, given a 64-bit number, I will block and do nothing for this amount of time, and that's it. So this is the entirety of the time module. There's no need for any other system call interface and so on later on. So we have this nice abstract code that takes time as a signature. And OCaml, the module system, lets you kind of layer and stack these on massively. So we have hundreds of modules in Mirage like this that describe the small pieces of operating functionality you need, and then you depend on just the functionality that you need afterwards, and nothing more. So we're building up functional abstractions where our device drivers, our libraries, have been replaced by flat libraries written in C to libraries with the richness of a functional programming language and with all of the abstractions and power pursuant within. How do you actually use this? Well, I'll talk to you more about this in the next few lectures, but fundamentally, from a user perspective, none of you in this room, except for 4 or 5 of you, have built operating system kernel patches in the past. With that nice abstract code parameterized across the operating system features it needs, all I have to do is type in Mirage configure Unix make, and that'll just give me a Unix binary. You can run on the Mac, or you can do one on Windows as well. And then I can just say configure for Xen, and it recompiles everything. It links in, it discovers all the device driver libraries it needs, and it builds an entire unikernel from scratch as well. At no point did you have to know the difference between the two, because the abstraction of the code you've written is so powerful. And when you run the Xen version, well, almost all of the code is in OCaml. It's running on the hypervisor, and it's all being optimized all the way down the stack. So we've built a functional operating system with just this recompilation. It's like recompiling it for an iPhone or something instead. And there's some really cool things you can do with these things. So the first one, if I have net access, you can actually store them in version control. So let me show you the live Mirage website. What are the chances of me crashing the Mirage website now? Let me see if I can get this to work. So I'll make this bigger. Let's see, I have to. We are connected. Can you all read the screen? Okay, so the Mirage website is running here. Unikernels can spin up and down in milliseconds, and for various reasons, the Mirage website keeps getting attacked. So this is the 15,000th instantiation in the last few days, and it's running. It's been running for a few seconds. I can see. how it's running, so you can see the logs and so on, and this is running as a specialized kernel. There's no Linux involved here whatsoever. From the outside world, I can just go to mirage.io, and so whenever you access that, it's being very slow because I'm connected by eduroam, which might not be working. So whenever we connect it to that, you can actually see the connection coming through there. So everything from our connection to there is being handled by OCaml code all the way down through the stack, and is written in the style of building as a unikernel. Now, how big are these things? Well, why don't we just take a look? So if I look at this Git, how many of you have used Git in the past? Okay, all of you. This is Git log. So every time we make a change to the website, we thought, let's do a little bit of a stunt. Let's compile a new unikernel, but we'll optimize it like crazy. So even the web pages are compiled into the unikernel and optimized. So it doesn't have any notion of dynamicity at all. It's all being built. And then all the images, compile them into, and then run it through something called Travis, which is an open source continuous integration system, and check the binaries into Git as well. So you can see for the last, I think 4 years, we've just been checking in all of our changes to the website, compiling a unikernel for Xen, and then putting it on the website. And this means that we can track every single line of code that goes into the website by the hashes. I'm just going to pick a random one, hope that it's useful. And so we track every bit of source code, and we can track its configuration, for example. Let me just pick a better one that is more interesting than just the configuration. The only problem with Git is you have to deal with hashes, and these hashes never make any sense. So here, for example, we have the configuration, and I'll talk more about that later on. We've got the actual unikernels. So if I look at Open Mirage, for example, it is this is the entire operating system that's running it. It's completely type safe, and we can reconstruct this operating system because the whole thing's version control. So we've moved not only from the actual configuration being stored, but also just checking the entire outputs. They're just a few megabytes in size, including all of its dependencies into version control. So it's kind of nice. So you can just do that. Now let me figure out how to get my cursor back, which is the biggest challenge. Okay. It's also type safe down to the device drivers. So building all these low-level device drivers is entirely possible in OCaml, and indeed in Haskell and in many high-level languages. While they look complicated, if you break down the interfaces, it's actually not that difficult to write them in different programming languages. And also you can scale them to many different protocols and styles. So the biggest doubt, of course, when you're starting this effort is, well, you can do it for simple protocols like HTTP. Anyone can write TCP stack to start with. But what about the other million protocols on the internet that you might have to deal with as well? Things like the transport layer security, DNS, XMPP for chat, all of that kind of stuff. And so over the years, we've steadily been building up and accruing some of this work. And we have shown that you can build really quite complex abstractions with millions of lines of OCaml code and still result in these tiny little unikernels. But to recap, give you lots and lots of information in this first hour. We've been rebuilding the entire system stack in OCaml for the purposes of trying to re-examine what operating system interfaces look like, to go from the existing momentum of the low-level operating system interfaces from the POSIX style to these nice, rich, high-level modular style building things. And the essence of Mirage, the reason it's called Mirage is because it's simply a series of descriptions of interfaces, and it disappears. And then a series of libraries that implement those interfaces, but each of those are small, composable, tiny bits of functionality. And then a set of boot layers that will let you actually run on things like the Xen hypervisor directly, so you can build operating systems. But it's not just a matter of compiling down to Xen. What I'll talk about in the next few lectures as well is just the sheer diversity of places that you can use this approach of building stuff in. It's a really good arsenal inside your toolbox. So it's great technology. I hope I've convinced you that it is possible to build a functional programming operating system and have it work. If anyone wants to try it in the break, massive brownie points to anyone who does. Go to mirage.io and give it a shot. And in the next lecture, I'll talk to you about how we actually use this in industry to deploy onto billions of machines. Thank you.
Yep, on here.
Hello.
Is OCaml linkable against like standard C libraries?
Great question. So the question is OCaml linkable against standard C libraries? Yes. So every language has a foreign function interface. So what this interface does is it defines exactly how you connect to the binary interface mandated by the other language. So C has a very rich ABI. By rich, I mean extremely overcomplicated and very hard to use. But OCaml, it does. Almost every language has a C interface. It's standard because in order to interface with the operating system, the language needs to call a C interface. So no matter how academic the language, I was going to say Idris there. I don't know where Edwin is, but Idris isn't really academic anymore. It's built its own community. But even from the very early days, that could call into C as well, because you need to do that to make any network connections or make any fundamental calls. OCaml goes one step further, which I'll explain in lecture 3, which is building C interfaces is very, very complicated. So you can use a mechanism called stage programming to describe the interface and then to auto-generate all the code in order to interface with the gory details behind it. So you can build manual interfaces, and using a library called C-types, which Jeremy Yallop, one of my collaborators, built, you can actually bind to C libraries without ever writing a line of C code, which is almost magical. And it's generally my goal in life is to avoid writing C code ever again. I don't want to do that. So.
One more over here.
Which architectures are currently supported by Mirage or OCaml?
I guess it's more of a question of which ones aren't. The native code OCaml compiler supports x86, 32, 64, PowerPC, 64, LE, big Indian, little Endian, ARM 32 with all of the variants, and ARM 64 as well. We have an out-of-tree support for RISC-V, which I'll talk about in lecture number 3. So once you get native code compilation, you can compile OCaml to almost everything from 8-bit microcontrollers to very large systems. The problem is, what can you practically do with these systems, of course? And so that's where Mirage comes in, because conventionally, anyone could do a stunt and compile, it takes work, but you could compile it to a microcontroller. But then you'd have to hack and build your own tiny little networking stack and so on. So the things I described are, the compiler can not only boot on these architectures, it can also do useful things like networking and so on by giving you, and I've got a little Easter egg I'll show you in lecture number 3, which is the tiniest thing it's ever been ported to. But I think I might have lost it, so I need to find the tiny chip. It is a problem with embedded devices now. They are very slippery. So, but if I can find it in the break, I will show you our latest target.
Okay, in the interest of time, we'll leave it there. Let's thank Anil again.
Thank you so much.